Okay, so the second misconception that often happens when we're studying the movement of things on Earth as opposed to the movement of things in space is if something experiences a greater gravitational pull because it's larger, why is it that planets that are smaller tend to have a greater orbital speed and therefore a faster orbital period than planets that are smaller? For example, the orbital period of Mercury is approximately 88 days. Okay, and the orbital period of Jupiter is 12 years. So how is it that this larger object is moving slower and therefore takes longer to travel around the sun if the force acting on it is greater? And this is because there's another kind of variable at play here. When we look at orbital period, the formula for calculating orbital period is 2 pi times the square root of the radius cubed divided by the gravitational constant times the mass. Okay, and if we also look at the formula for finding the size of the force between two objects, it is the mass times the gravitational constant times the mass of the sun, but it's also radius squared. So the variable that we haven't talked about here is radius. And yes, Jupiter is larger, and so if that was the only variable that we were considering was the size of the object, it would have a gravitational force. But the other thing that we need to consider is that there is a difference between the distance between Mercury and the sun, or the radius, and the distance between Jupiter and the sun. And the effect of the distance on the force of gravity is going to be greater because the mass is just a straight variable and there's nothing done to it, but the radius at the bottom of the formula is squared. So yes, increasing the mass by itself and not changing the radius would result in Jupiter having a greater force, but because its distance is also about 15 times greater than Mercury and that number gets squared, right, the force acting on Jupiter is actually going to be smaller, which is why it ends up with a longer orbital period and why we also have to consider the distance between a planet and the sun, not just the size of a planet when we're talking about orbital period and also when we're talking about orbital speed. The other thing that gets slightly confusing in this is why is it that objects are moving at different speeds at different times? If the mass of the object is consistent and the mass of the sun is consistent, then the force acting on the object should also be consistent, and therefore the acceleration of the object should be consistent as well, just like objects on Earth, right? The force that is being exerted on the objects on Earth is constant, and so their acceleration is always the same. However, again, the difference here is because the force of objects on Earth don't experience the effect of radius. And the radius, which is the distance between the center of the sun and the center of Jupiter, actually changes at different points during its orbital period, right? Objects that orbit the sun orbit in what's called an ellipse, which is very similar to a circular shape. So a lot of those circular motion formulas still do apply, but it's slightly different because objects that orbit around an ellipse actually orbit around two centers of axis, not just one, like you would for a circle. And one of these axes is the sun. But as you can see, because the sun is not completely in the middle, it's not that central axis of rotation, the distance between the sun and the object at one point is going to be a lot smaller than the distance between the sun and the object at the other point of its orbit. So the mass is not changing in this case, but the radius is getting larger or smaller, and as a result, the force of gravity is going to get larger and smaller as well. So when it is closest to the sun and has a smaller r, or radius, it will have a larger force of gravity. And when it's farther away from the sun and it has a greater r, it's going to have a smaller force of gravity. And if we are applying a large and small force to the same object, which is the planet, whose mass doesn't change, that's going to result in a larger or smaller acceleration. So the greater force you apply to the planet, the greater its acceleration will be. So here where we're very close to the sun, it will have a much larger acceleration than here when we're very far away from the sun. Okay, and the last thing that I wanted to discuss, or the last kind of thing that tends to confuse people, is why is it that when we're calculating the orbital period of an object, we only take into account one of its masses. So the formula for our orbital period is the square root of g, which is the gravitational constant, times the mass of one of the objects divided by the radius. And so a lot of times students get confused and are trying to figure out which mass are we talking about with this formula. Are we talking about the mass of Mercury as it orbits around the sun, or do I need to find the mass of the sun? And again, as we talked about in the last lesson, the mass that you're trying to find here is the mass of the object that it's orbiting around. And that's because if we want to find the speed of an object, essentially what we're trying to find is the acceleration. Right? If an object accelerates more, it's going to have a greater final speed or a greater average speed than if an object is accelerating less. So here we're trying to figure out acceleration. Acceleration is going to be equal to force divided by mass. If I plug in my formula, divided by for calculating the gravitational force between two bodies, which is g times m1 times m2, and then I divide it by m and radius squared, or divide it by radius squared and then multiply that bottom part by m, because that's the bottom part of this formula. I end up with the formula g times m1 times m2 divided by m1 times r squared, right? So because m1 is on the top and bottom of the fraction, I can get rid of that part. So the acceleration of objects in space is really only equal to the gravitational constant times the mass of the sun divided by the radius squared, which is where I end up with this formula. And this formula is slightly different because it's calculating speed, not acceleration. But again, you can see that it's only dependent on the gravitational constant, the mass of the object that is being orbited, and the radius between the two objects. Hopefully that clarifies some of the kind of misconceptions that can come in with this unit. If you're confused about any of the other kind of conceptual ideas that we've been talking about in this unit, please make sure to let me know, because we will be assessing these on the test as well. Okay.